Instance of Physics Friday here, where every Friday I go vertical live stream and talk about whatever physics is on my mind, which, uh, you know, is usually not all that focused, especially since it's between the hours of when I have, I don't know, no peanut gallery to when I have peanut gallery again. Um, I don't know. I was thinking a lot about the ways people think about special relativity, because I have my only paid gig at the moment is I have one tutoring student, which you know uh, is actually kind of nice because it's I have a you know just enough to do sometimes to feel like I'm being productive, but I'm keeping my stress level low given disasters that have resulted in more 5150s than I'd like in the past. But anyways, I was thinking back to my own undergraduate education and a lot of other things, and the extent to which, like, I've sort of joined the conversation in the past about this whole thing about, like, whether or not you should talk about, non-constant mass in special relativity. Um, it, 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 it is somewhat debatable. Um, like, the thing that should always be emphasized is that rest mass is invariant, and the question is there any other mass besides rest mass that is ever relevant? And the short answer is no. The long answer is it's complicated. Um, the real origin of why people talk about non-constant mass is because of synchrotrons, right? Um, as a charged particle gets closer to the speed of light, the electrical charge that it has remains constant. But if you use a magnetic field to send that charged particle in a spiral, the way they do in a cyclotron, right? In a cyclotron, not a synchrotron, you can use a constant frequency of electromagnetic energy to accelerate the particle, because the radius will depend on the speed, but for speeds far from the speed of light, the amount of time it takes to go around one circle is actually constant, because the radius is proportional to the velocity, and so that implies that you have a constant angular velocity. But as you approach the speed of light, that is no longer true. Right? So that's why people originally started talking about, like, effective masses near the speed of light, even though if you really want to think about it properly, there is no such thing. And there's a bunch of ways that you can think about the ways in which the acceleration of a particle close to the speed of light is not what you would predict using non-relativistic equations. You can think about it in terms of time dilation in the rest frame of the particle. Smiley face, hello. So you can think about it in terms of time dilation. You can think about it in terms of electromagnetic fields transforming in different reference frames. You can, and even though it's ill-advised, think about it in the way that becomes controversial, where you talk about it in terms of the effective mass changing, even though it really doesn't. Or you can just think about it as acceleration no longer being equal to force divided by mass, right? The force as measured in the lab frame divided by the rest mass no longer gives the acceleration in the lab frame. That is, I think, a sufficiently carefully worded statement that it always holds. But I tend not to think about it in terms of the way I think about it probably most closely resembles time dilation. Because I tend to think about it in terms of, right, it's like, to me, the most intrinsic way to think about special relativity is events, right? Is to think about things in terms of causality, right? Because you can disagree about how long it takes for something to happen. What you cannot disagree about is the order of events that are inside of one another's light cones, right? Which is to say, the order of events that can actually affect one another. Because events that are too far apart relative to when they happen to affect each other, you can kind of think that they happen whenever you'd like. Well, not whenever you'd like, but it can be completely frame dependent when events occur if they're what we call space-like separated, but not if they're time-like separated or light-like separated, right? Then you have to agree on which event happens first, because they can actually affect each other, and that means that, reality is ultimately not relative, right? Reality has to just exist. But the exact amount of time something takes, or the exact amount of space between different things, that can depend on your reference frame. And so when it comes to something like a charged particle in a cyclotron or a synchrotron, you have to agree on things like how many times does the particle go around in the cyclotron or synchrotron before it ultimately exits, right? You don't have to agree between different reference frames on how long that takes, or how fast the particle is going, or things like that. And so it is ultimately better to just think about the mass as the rest mass, and to think about the acceleration as being frame dependent. And of course, this is one of the things where it's like, bear in mind, the particle's reference frame is not overall an inertial reference frame, because it is accelerating, but you can always take it back to thinking about a locally inertial frame. That question has nothing to do with what we're talking about, but no, it is never okay. Except, obviously, if it's in some sort of self-defense. But anyways, I hate the internet sometimes. So anyways, it's really better to think about God, I hate the internet. Oh boy. Anyways, so to agree on is, what am I yapping about? The thing that is the title, physics. And we are talking about special relativity today because I was recently tutoring a student about space-time intervals, which I think is one of the best things to think about to understand relativity, because people sometimes get sidetracked by this debate about whether or not you can talk about non-constant mass. And to be clear, I come down in that debate on the side of, you really shouldn't. You should think about the rest mass as being the only mass that you should really talk about for a particle. You can talk about a, like, effective mass, quote unquote, in other reference frames besides the rest frame of a particle that is greater than the rest mass, but it's always kind of fictitious. And what you should really think about is what is the trajectory of a particle through space-time, and what aspects of that trajectory have to be universal between different reference frames. And the answer is that you can disagree about how much of a trajectory is space and how much is time, but you always have to agree on what they call the space-time interval, which is this quantity that's the time squared multiplied by the speed of light squared minus the distance squared. And if that quantity is positive, then the events are what we call time-like separated. And those are the events where we all have to agree which ones happen first and which ones happen second, or which ones happen later, or which ones happen earlier. Because events that are time-like separated are, right, what this interval is measuring, right, is it's basically, it's measuring how are things separated relative to the trajectory that a particle traveling at the speed of light would undergo. Right, so things that have a space-time interval of 0 are things that are separated in a way that could be exactly traversed by a massless particle traveling at the speed of light. Things that are time-like separated, where the speed of light squared times the time squared is greater than the distance, right? That means that there's enough time that a particle traveling slower than the speed of light could traverse the trajectory, and therefore they can affect one another. And so if it's equal to or greater than 0, then different events on that trajectory can affect one another. Different events with that separation can affect one another. Any trajectory that ends up with space-like separation is a trajectory that an individual particle cannot traverse. You could draw it out as a world line, right? You could imagine such a trajectory, but it could never be traversed by any particle, even a massless particle. But a space-time interval that's positive or 0 can be traversed. Oh, there's the cat, or a cat. We have 3. Look at her go! Run, run, run. So yeah, I think it's really better to think about that space-time interval than it is to try to think about mass, because in summary, mass is only ever the rest mass. I know, cats are wonderful. Mass is only ever the rest mass. Good Lord, I hate the internet. Alright, you know what? That'll do for today. Peace out, y'all.